Now this session is about horizontal and vertical tangents. Now we have the special cases where one is a horizontal tangent, a tangent parallel to x-axis, and a vertical tangent, a tangent which is parallel to y-axis. So let's see what are the types of how many tangents we exist in the form of horizontal and vertical tangents for the hyperbola. Say for example, I have the standard equation of hyperbola in this form. Now we see that this extends till infinity out here on the left, and this extends till infinity on the left here and on the right here. Is how we see the hyperbola extending outwards there. So clearly we can see that any line I draw, I don't have a horizontal tangent, because at some point this tangent has to cut the hyperbola, because hyperbola extends itself on the right side and on the left side. So we cannot get horizontal tangent which can be drawn out here, so that this cuts clearly one of the hyperbola somewhere. So a tangent drawn is not possible horizontally or parallel to x-axis, either on the upside or downside. So this makes us conclude that there exists no horizontal tangent for the hyperbola. So there exists no horizontal tangent for the hyperbola, because it has to cut the hyperbola at some point at the right or the left. Now let's see similarly for the vertical tangents out there. Clearly I see that any tangent I draw at any of this point has been not parallel to y-axis, but there are two tangents particularly which are parallel to y-axis. That is, if I take the vertex A and A dash, any tangent I draw through A is parallel to y-axis, and any tangent I draw through A dash is also parallel to y-axis. So these two are parallel to y-axis. Therefore, there exists no horizontal tangent for the hyperbola, but there are two vertical tangents for the hyperbola. There exists two vertical tangents for the hyperbola. So these are the two vertical tangents, T1 and T2, as can be seen in the diagram. So this makes us conclude that for an hyperbola there are no horizontal tangents, but there are two vertical tangents at the vertices A and A dash. Is how we conclude the concept of horizontal and vertical tangents for the hyperbola. Asymptote. Now next we are going to discuss about asymptote of a hyperbola. Now what do we mean by asymptote for the hyperbola? The word asymptote plays a vital role in the graphing concept of mathematics, and here let's discuss about asymptote of a curve. Say for example, if I take a curve and I take a line. Now as I see here, as the curve proceeds on the right and the line is proceeding equally on the right, we see that there are some graphs and lines which behave in a way where the line tends to touch the curve but never touches. That is, as I move further and further, I see that the graph tends to get closer and closer but never touches. This is how I see that the graph never touches, but they have at least some minute distance between them, which makes that called asymptotic behavior. This kind of a behavior of a line with respect to the curve is called asymptotic behavior, and this line is called asymptote. So mathematically we define an asymptote as a line which tends to touch the curve but never touches. So here for this example, this line L tries to touch the curve, but it doesn't touch, almost getting closer and closer is how we identify its property. So as we move towards infinity, even the curve moves to infinity, but they get closer, but they never meet. So mathematically we say that an asymptote tends to touch the curve at infinity, but in general sense they never meet, is what is called an asymptote. A line which tends to touch the curve but never touches is called an asymptote. In this case, this line L is an asymptote because it tends to touch but never touches this curve C. Is how we understand the asymptote for a given curve. Now let's discuss about the asymptote of a hyperbola. Because the topic is about hyperbola, let's discuss about asymptote for an hyperbola. Now we have two cases which arise in case of discussing the asymptote for an hyperbola. Now case 1, where it's a non-vertical line and vertical line. So an asymptote is a non-vertical line if suppose y is equal to mx plus c will be an asymptote for the hyperbola y equals f of x. This line is an asymptote for this curve if the difference of mx plus c, the difference of f of x minus mx plus c tends to 0 as x tends to plus or minus infinity. So here we say that the non-vertical line is an asymptote for the curve if the difference of curve minus the line tends to 0 as x tends to plus or minus infinity. Is how we understand the non-vertical asymptote for a given curve or to the hyperbola y equal to f of x. Now similarly, let's see the vertical line being an asymptote, that is x equal to plus or minus a. One is a on the right and one is a on the left. So is an asymptote for the curve y is equal to f of x if mod f of x tends to infinity as x tends to infinity. Is how we understand, or x tends to a. Is how we understand the concept of the vertical line being an asymptote. Therefore, we have two formulae. One is a non-vertical line will be an asymptote if this tends to 0 as x tends to minus infinity, and the second case being that this will be an asymptote for this as the vertical line if this tends to infinity as x tends to plus or minus a. Is how we understand the vertical asymptote and a non-vertical asymptote. Now let's see an example problem. Say for example, I have the line y is equal to x and the curve y equals x plus 1 by x. Then I would like to know the asymptotic behavior of this with respect to this curve. So similarly, in this case, we use the property of case 1 where this is a non-vertical line will be an asymptote for this curve if I consider x plus 1 by x minus x is equal to 1 by x, because x and minus x get cancelled. So this minus this is 1 by x. That is, this clearly tends to 0 as x tends to plus or minus infinity, because when x tends to infinity, then it's 1 by infinity is 0 and 1 by minus infinity is also 0, which I have applied here. Therefore, 1 by x tends to 0 as x tends to plus or minus infinity. Therefore, y equal to x is a non-vertical asymptote for the curve y equals f of x, that is x plus 1 by x, is how we understand the non-vertical asymptote for the curve y equals f of x. So now that we have discussed about asymptotes for the curve, let's see what are the asymptotes for the hyperbola. Now we see that there are two asymptotes, two non-vertical asymptotes for this hyperbola. So let's take the standard form of hyperbola, which says x-axis, y-axis in this form. So here I have two asymptotes, one passing through origin and looking like this, so there are two asymptotic behaviors at the curve here. This is where the graph tends to touch, and here where the graph tends to touch the line, and here and here. So this line L1 and L2 are called the asymptotes. L1 and L2 are non-vertical asymptotes for the hyperbola given in the form x squared by a squared minus y squared by b squared equal to 1. So these two asymptotes are given by the equation y equals plus or minus b by a of x. So these are the vertical asymptotes, where one of them is given by y equals plus of b by a of x, and this is given by y equals minus b by a of x, is how we understand the asymptotes this and this for the given hyperbola. So asymptotes for a standard form of hyperbola are y equals plus or minus b by a times x. Now that we have seen the two asymptotes for the hyperbola, we clearly see that the two asymptotes pass through an origin. So asymptotes L1 and L2 pass through origin is what we identify in these two cases. And also we see that their angular bisectors is same, that is, the angle made by this is theta, then this is also theta. The angular bisectors are same, that is, the x and y axis bisects the asymptotes for the angle theta and theta out there, and therefore we have this angle equal to this and this angle equal to this, or if I take this as alpha, then this would also be equal to alpha, is how we conclude the two geometrical properties. One is passing through origin and the other is making equal angles or angular bisector. Now suppose we take The conjugate hyperbola, which we know is given by equation x squared by a squared minus y squared by b squared equals minus 1. So for this conjugate hyperbola, let's see what are the asymptotes. That is, if I take the conjugate hyperbola this, then its asymptotes are given by just equating this to 0. That is, the asymptotes for conjugate hyperbola are given by the equation this equal to 0. That is, when I take this in the form x by a whole square minus y by b whole square equal to 0, then this is x by a plus y by b times x by a minus y by b equal to 0, which on splitting gives equal to 0, are the asymptotes which are passing through origin and approximately with the asymptotic behavior. Is how we get L1 and L2. This is given by L1 and this is given by L2. Is how we get the asymptotes for the hyperbola, given by this and this. For the conjugate hyperbola, x squared by a squared minus y squared by b squared equals minus 1. Now let's see the relation between equations of asymptotes and equation of the hyperbola. So for example, I have the hyperbola x squared by a squared minus y squared by b squared equal to 1, and we have identified the two asymptotes for them as y equals b by ax and y equals minus b by ax. That implies I get this as y minus b by ax equal to 0 and y plus b by ax equal to 0. That is, if I combine them, I get this to be y minus b by ax times of y plus b by a times x equal to 0, which on simplification gives a squared minus bx by a whole square equal to 0. And dividing by b squared, I get y squared by b squared minus x squared by a squared equal to 0. That is, I get this to be x squared by a squared minus y squared by b squared equal to 0. As I observe here, I see that my equation of hyperbola is this, and my equation of pair of asymptotes, equations of pair of asymptotes is given by this. I clearly see that the right hand side differs by a constant. So this is equation 1 and this is equation 2, implies therefore equation 1 and 2 differ by a constant. That is, the pair of asymptotes always differ by a constant, here equated to 0. Therefore, equation of pair of asymptotes differ by a constant. equated to 0 is how we understand the equations of the asymptotes and equation of hyperbola connected through the constant. If I equate the right hand side constant of the hyperbola to 0, I get equation of pair of asymptotes. That's how I understand the relation between the asymptotes and the hyperbolic equation. Now let's do one practice problem to understand the concept of hyperbola more better. As that we have discussed about eccentricity, foci, lattice rectum, vertices and other properties like length of lattice rectum for the hyperbola in standard form and non-standard form. Let's try to apply in doing some problems and to understand the concept more better. So for example, the question here says find the center, eccentricity, foci, directrices and the length of lattice rectum of the hyperbola given by equation 4 times equals 1. So is how we get the whole of equation of hyperbola given in this form. Now let's try to see how we can find the center, eccentricity, foci and other properties for this. So as I have the equation here, let me arrange in the form is equal to 1. Now I want to divide the whole equation so that I get it in the form of x squared by a squared minus y squared by b squared equals 1. I take minus common, is equals minus 1. And then if I further simplify this to get into the standard form, I get this as x minus 2 whole square times 1 by 9 when 9 comes to the denominator and minus of y minus 3 whole square by 1 by 4 is equals minus 1. Now clearly I see that this is a conjugate hyperbolic equation because the right hand side is minus 1. This is a conjugate hyperbola. So with this conjugate hyperbola, we find the vertices, the foci, the directrices and the length of lattice rectum for this equation given in conjugate form. So let's see how we can do each of them. Now clearly, as I see here, my A derived out of here is 1 by 3 and my B out here is 1 by 2 when I raise this to the square. Now clearly I know that 1 by 3 is less than 1 by 2. That implies A is less than B. So for A less than B, the condition is that the hyperbola has this, where the conjugate hyperbola lies out here because its original hyperbola lies on the top. Okay. Now here I have each of this in the standard form, where if I want to find the center of this, then we have this x as x minus 2 and y is y minus of minus 3. That implies h is 2 and k is minus 3 is what we get. So using the value of h and k to find center, I have center is obtained by 0, x minus 2 is 0, so 2 and y minus 3 is k. So center is hk is what we get because I take x as 0 implies x minus 2 is equal to 0. That implies x equal to 2, and y equal to 0 implies y minus of minus 3 is 0. That implies y equals minus 3. Therefore, I get 2 and minus 3, which is the center of the hyperbola, the conjugate hyperbola given by this. The case a less than b gives me the conjugate hyperbola here and the original hyperbola on y-axis is what I get. So my center is 2 minus 3. Next, to find the vertices. So to find vertices for this conjugate hyperbola with condition a less than b, I have my vertices clearly here as a and a dash. So in this case, my a is given by a0, that is x minus 2 equals a, that is 1 by 3, and y minus 3 equals 0 is what we get. Now in this is 2 plus 1 by 3, and this is minus 3, which on simplification gives 7 over 3 and minus 3. Similarly, my a dash is 2 minus 1 by 3 and minus 3, which on simplification gives and minus 3. So the coordinates of a are 7 over 3 minus 3, and these are 5 over 3 and minus 3 is what we get for a and a dash as the vertices. Next is to find the foci, that is my s and s dash. My s and s dash. Now clearly we know that the foci are given by AE, 0. Therefore, my x coordinate being x minus 2, I get 2 plus AE, that is 1 by 3 times of E, which I am going to find using the formula root of a square plus b square by a square is the eccentricity by b square, because a is less than b. The eccentricity formula is given by this, so which on simplification gives root of 1 by 9 plus 1 by 4 by 1 by 4, which on simplification gives 36 So this is root 13 by 9, which I get as root 13 by 3, y, which is minus 3. So my focus is what I get in terms of root. Similarly, my other focus s dash is given by 2 minus 1 by 3 root 13 by 3 minus 3, which on simplification gives 9 to 18 minus is what are the foci s and s dash, that is s given by 18 plus root 13 by 9 minus 3, and s dash given by 18 minus root 13 by 9 and minus 3 is what we get for s and s dash, with eccentricity as root 13 over 9. Now next is finding the equations of directrices. So suppose I have a directrix out here and a directrix out here, then equations of these two directrices are given by the equations x equals plus or minus a by e, one given by plus and one given by minus, that implies x minus 2 is plus or minus a by e. That implies x minus 2 is plus or minus 1 over 13. That implies x is 2 plus 1 by 13 and x is 2 minus 1 by root 13 are the equations of directrices as we see here. So 1 given by 2 1 by root 13 and the other given by x is 2 minus 1 by root 13 is how we understand the equations of directrices for the hyperbola in transformed form. Next is length of lattice rectum. Now, in case of length of lattice rectum, we see that lattice rectum is a line which passes through focus and is perpendicular, that is L, L dash. Even the other lattice rectum being MM dash. So there are two lateral recta, L, L dash and MM dash. That is, the length L, L dash is given by the formula 2b square by A. That is 2 times b square of this by A, which is this. So this gives 1 by 2 times 1 by 3, that is 3 by 2 units. Therefore, length of lattice rectum is this units. That is, this distance is 3 by 2 units as we see here. So this is how we find each of the foci, the directrices, the length of lattice rectum, the vertices, or A, B and eccentricity each of for the respective hyperbola in transformed form in this example problem.